Hey guys, how's it going? So, I am making this video to kind of help you understand a little bit more about kinetics, about collision theory, about why kinetics actually works the way it does. So, there's this nice little PhET simulation here. I'll have a link somewhere. Look it around, probably on the calendar. But if you just look up PhET, P-E or P-H-E-T, you'll find a whole bunch of these simulations, and you look for the reactions and rates one. So this is the reaction that we're going to be after right now. A plus BC goes to AB plus C. All right. So here is this thing. And basically, remember, the only way we can get these guys to swap is if A slams into B in the right orientation and with the proper amount of force. So if I put a little bit of force into this, real quick, remember, force is, reset, reload. Remember, force, in this case, kinetic energy, is temperature. So if I put a little bit of kinetic energy in this guy, boop, and now it's at a certain temperature, certain kinetic energy, not much is happening. They're bouncing around, they're bouncing off of each other. Bop, 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 but not anything is happening. So remember that in order for this reaction to take place, it has to hit the right orientation. Well, the orientation is right. A is hitting B, so that's bueno. But what isn't happening is that it's not hitting with enough force. Okay, we need to start thinking about the energy diagram here. And as we can see here, we have this amount of energy going on with the molecules, and it's not enough to get over that activation energy. So one thing we can do is increase the temperature, increase the kinetic energy. So if I stop here, this is the potential energy of our products. Of our products. And even then, even if I do this, it's just going to come up to this point and fall back down. In fact, I can even look at this little separation view. Let me pause it. So if I kind of step forward, we see them getting closer and closer. And they will actually hit, but they won't get any closer than this, and there's not enough energy for any of the reaction to take place. Then it falls back down. Okay. Get you going. So let's raise the temperature up a little bit more. Even at this point, it's still just hitting this point, not jumping over. So let's kind of raise it up even more. Boop. And there we go. So let me kind of stair step it a little closer. Talk about this a little bit more. So it's getting closer, 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 and it reaches this point at the top of that activation energy. This is the transition state that is there. This is basically kind of that weird thing that shouldn't exist. Right now it's ABC all together, bonded together. So yeah, that shouldn't exist, and it doesn't like to exist. So it's going to fall back down one way or the other at this point. It's going to either move toward the products, or it's going to fall back down to the reactants. In this case, it fell back down to the products side of things. So does that. Now if we let it just keep on flipping around, it's going to flip back and forth. Boop, 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 boop. Okay, we can actually lower the temperature, and if we lower the temperature to where they're no longer hitting with a significant force, it's now going to be stuck in this product side. Okay, awesome. Great, grand, wonderful. You can go through, and I highly suggest that you play around with this. You can try different reactions. Like, what is this one going to look like? Okay, if I let me lower the temperature down. As soon as I put any amount of force into this whatsoever, it's just barely going. Temperature is barely there, and then all of a sudden, boop. And now popped back, because here's this total amount of energy, kinetic energy here. Wait for it, And down here, and it pops back. All right. So this is what's happening when there's a single collision going on. But what is it going to look like when you have a lot of collisions? It's going to be the same thing, but remember that this is the total average energy. If this is the average energy, remember what it's actually going to look like. It's going to be this distribution of kinetic energy. These guys are moving, or the speed here is going to be pretty high. And this is the average here. So some of these guys are going to be going faster. In fact, if I do this right here, some of these guys, this total that are moving around, are going to have enough energy to bounce over. Not very many, though. Let me go through. This is fine. Let's say 20 of each. Okay. Go. I said go. There we go. All right. Now it's going. Now you're looking around, looking at this, and you can see not much is actually happening here. Not a lot of them are changing. That's because the kinetic energy is pretty low. I'm going to add in a bar chart here so we can actually see them changing, if there is any. And we're not really seeing much going on. So what I'm going to do is raise that temperature up. Oh, there we go. Okay, I just added a little bit, and there's a little bit more has come through. So we've moved this reaction closer to the product side with that. I can raise this a little bit more, and if I do that, it won't take nearly as long for more to hop over to the other side. Okay. Now here's the thing, though. We know that. Let me switch to a different guy. There we go. Let's do the same idea here. Okay. Where it should automatically, as soon as any of them actually hit, it should move over to the product side. And it always wants to be down here in the lowest potential energy. So it should, all the products should be at the lowest potential energy. That's where it's going to head out. So let me kind of do 20 and 20, go. And you can see that really quickly, it just zip, started moving down and started gathering up a bunch of products. Okay. There's that. And if I lower this down a little bit more, it's going to be harder for these guys to become reactants again. Okay. Clear that container. Let's do this. Initial temperature right around there. Let's do again another 20, 20, go. See what happens. So they're bouncing around. Some of them are actually getting over. And it's going at a certain rate. It's flipping over to this side at a certain rate. In fact, if I do this, kind of clear and start over again. We can see what's going to happen. We should see that these products going up and the reactants start going down as they are moving around. And this is happening at a certain rate, right? Now you can think, what are some things that are determining this rate? Well, one thing is for sure, if I were to kind of reset this, do 20 and 20, I'm going to pause it. If I increase the temperature up to here, that means it's going to be going faster. They're going to jump over this activation energy at much faster than if they have it very cold. So in fact, if I do this and I play it, forgot to get these going. 20, 20, go. Now if I just wait here and see what happens, you can see not much is going on. It's going to take a long time for these guys to actually jump over. But if I just sit and wait and just kind of sat here, eventually one of them's going to hit with a right amount of force and the right amount of orientation and everything. Because some of these guys are moving fairly quickly. Let me actually put this up a little bit hotter. About to here. 20, 20, go. All right, let's see this go. Oh, already one of them has got, two have gone through now. 3, 4. So now it's actually starting to go down. We actually had a bit of rate there. And now when the concentration of these guys change, there's less of them, less likely for it to actually get a collision. So the rate of change is decreasing. So back here, yeah, there were a bunch of them. Of course they were going to hit, and actually, you know, the likelihood of them hitting is pretty high. Now that there's less of them, it's less likely for them to actually hit. So the rate is a lot lower. Okay. So there's that. Let's kind of do this exact same thing, but let's change the concentration here. Let's actually do 100, 100, and go. Let's see what that rate is. Move this to 100. There we go. You can see that the rate, the amount that's changing, is a lot higher. This rate is, this slope here is a little bit steeper. It's taking about 100 seconds before things start evening out. If I go through and let's clear this container and let's just do like 10 and 10. So this should be 10 times as long. So we should have to wait until about 1,000 seconds before things start leveling out. Let's see what happens. Make this graph a little bit closer. There we go. So we should start seeing them really leveling out after about 1,000 seconds because it takes 10 times as long. I know that this is a second order reaction because it's two molecules hitting together. Single step, one mechanism, nothing crazy going on. All right. Almost. See, it's taking a lot longer now for it to actually level out. Okay. So what I want you guys to do is kind of start playing around with this a little bit. Look at some different energy profiles, some different temperatures. No real, like, I want you to just kind of play around with this and figure out what is happening. You know, sometimes this is the, oh, there we go. Oh, right at 1,000. That's whenever they start getting to that point. So yeah, this is kinetics, right? That's what you would imagine. Okay, now rate experiments. This one, let me kind of reset everything here. Here you can go through, do the exact same thing. Set up before, set up the here. You figure out how many you're going to start. You can hit stopwatch, and you can even go through and start a stopwatch here to make sure you get your kinetics data in. Let's see, how many you want to start with? With this scenario, I want to have it start about here. I don't want any on the reactant side, but I want, let's say, 10 and 1. Begin experiment. See what happens. How long is it going to take? Oh, there we go. We now have our one product. Will it go back. But yeah, you can kind of mess around with this. So let's turn that to 10. Begin experiment. Go. How long will it take to kind of reach equilibrium? Now, we haven't talked about equilibrium yet, but this is also going to give you a good idea on what an equilibrium is. Essentially, an equilibrium is when things don't change anymore. Remember, they kind of were going back and forth between products and reactants. This is a reversible reaction. And when you do that, equilibrium is like right now, where it's not changing at all. It changed a little bit there. And now it's back. So yeah, they kind of go back and forth. It's kind of 5 and 5. That's what this one is. There we go. So, this is a little demonstration I wanted to show you guys. Look at this, play around with it, see what's going on. If you, hopefully you can kind of get a feel for what these energy diagrams actually mean. Yeah, try and, play with it. Try and break a reaction. All right. Don't forget, I'm also going to put out this, where did you go? This worksheet. Fill it out, look through it. If you have questions, write down the questions because we're going to be going over this on Tuesday. Tuesday the 2nd. Tuesday the 2nd. All right, guys. Have a good one. See you guys later.